Today we'll be learning about astrophysics and cosmology in the AI era. So astrophysics is very near to my heart, and cosmology. I love cosmology. I took a class on cosmology in grad school, and it was one of my favorite classes. And the big thing about cosmology is everything, I feel like, assumes very large scales. So like everything is valid on the scales of like 1 megaparsec. I forget exactly what a parsec is. I think it's like 10 to the 19 miles or something like that. And then, so it's like, it's for you're thinking about things in the universe and the evolution of the universe on extremely large time scales, which I think is pretty cool to think about. And AI is obviously, it's a buzzword these days, but you'll get a sense of what that actually means and how we use it in particle physics and in cosmology to help solve the problems that we're trying to solve. So yeah, I think that's enough from me. I'll let Alex get into it. Yeah, enjoy.
Cool, thank you. Nice to see everyone here. Okay, so let me see. Yeah, I wanted to start with just a couple of slides about me, so you get a picture of like how I got here and why I'm talking about the things that I'm talking about today. So let me see if the clicker still works. Let me see. Okay, cool. Okay, so I'm from Europe. I studied everything, so undergraduate studies, graduate studies, high school, primary school, everything in Serbia. Serbia is here. It's a pretty small, landlocked, currently country in the Balkan region. So like probably you can recognize Italy and Greece. We go to our summer vacations there because there's a really cool sea over there. But for us, we're here. So Belgrade is the capital. And there I studied astrophysics undergrad and PhD. And this is the building of my university. I actually did that at the Faculty of Mathematics. That's kind of where astrophysics is placed, because astrophysics grew as a kind of a subfield from astronomy, and astronomers are mostly mathematicians. They deal with like the movement of celestial bodies and mechanics, and that was a natural thing to like kind of grow from people doing mathematics. So that's kind of, we have a very long history of this faculty, so kind of it grew there and stayed there. So we're not in the Faculty of Physics, although I did have all of my physics classes with the students from physics. And after I graduated and after I did my PhD, I worked there as several different positions, but assistant research professor was the last one. And I also worked in this even older building that's right across the street, which is the Serbian Academy of Sciences and Arts. And there is a mathematics institute over there. So people doing mathematics, computer science, and a few astro people also work there, especially because at that time I kind of started doing more machine learning. So it made sense for me to move there also. But eventually, around COVID time, so in 2019, I came to Fermilab. I started working with people from Fermilab already while I was in Serbia, and it was kind of a natural, just physical move for me. And yeah, my PhD initially wasn't about machine learning at all. It was more theoretical and observational astrophysics. But let's say like 10 years ago, maybe, I moved more towards computing and machine learning. It was still a very new field at that time. Of course, like there was some simpler forms of machine learning a lot earlier, but it wasn't really a thing in the sciences. Maybe it was kind of starting there. It was mainly because, and I will talk more about this, because of like the increase in computing power that we had, and hence also better algorithms that we could do. But yeah, that's kind of how I got here. But let's move to the topic that I want to talk about. So as you've seen in the title, I mentioned both cosmology and astrophysics, and I did want to differentiate between the two just so that you get a better picture of like what these two sciences that are complementary but not exactly the same, what are they all about. So for astrophysics, that branch of science, it studies astrophysical objects individually. So stars, galaxies, whatever you can find, black holes, even more like boring things like dust its composition, how it evolves, why it's there, even gas, different types of gases in space and why they appear, how they evolve, and so on. So it's physics of all of these objects individually in some way, or how they interact. Cosmology, on the other hand, thinks about the universe as whole, as one entity. So it thinks about much larger scales, and it tries to figure out why we are here. So are we alone? How did we get here? How did all of the everything in the universe came to be, and how it evolves, why it evolves, and how does the universe work? So how is it changing over time? What are things like, and you've probably heard about these terms like dark energy, dark matter, and how do all of these components and things that we can find in space actually influence how the universe evolves over cosmic time? So basically trying to figure out everything, but somehow make it a one theory, one thing to understand how the universe came to be, why is it the way it is, and what will happen in billions of years later. Right? And for us to understand these things, and even if you want to study any of the astrophysical objects, but this is particularly important in cosmology, is that there are like 2 or 3 main things that cosmologists use to try to figure this out. So we use data from experiments and from astrophysical surveys. So physics in space is the same physics that happens here. So we can utilize experiments here, like high energy physics experiments, to understand particular types of particles or dark matter, search for it, understand it. So both experiments in labs on Earth or telescopes to observe the sky are useful. Of course, there are many telescopes in orbit that we also use, but so all of this experimental and observational data is one piece of the puzzle. The other very important piece of the puzzle are simulations. Again, simulations of experiments and simulations of the things that happen in space, but also simulations of the whole space. So there are simulations, very big like boxes of fake universes that we can simulate because we know the main driving forces behind, what drives the evolution of the universe, and we can make a box of a fake space that evolves over cosmic time and see how galaxies form, evolve, interact, and see if that matches what we can see and observe with our telescopes. And that way, because we know what goes into the simulation, we can see if our interpretation of physics currently is correct, or if there's something missing, and how to try to figure out what's missing. But in recent years, artificial intelligence has become very important. So artificial intelligence helps us work with huge data sets, and we have huge data sets both from simulations and from observations. So we're kind of really lucky to have these really cool new tools to help us figure out how to understand these data sets, how to search for interesting or weird, rare phenomena in these data sets, which is very tough without it, honestly. It's many things, especially if you're searching for rare phenomena, you need a lot of people searching through billions of images or whatever, spectra or things like that. So that is becoming more and more difficult because our data sets are becoming larger. So let me start. So the idea for this talk is basically in the first hour, I'm going to talk more about astrophysics, cosmology, and like what we know about the universe currently. And then in the second half, I'm going to talk a little bit more about AI. So let me start with a brief overview of like the history of how we view the universe and the skies in general. Because I want to start with this very distant moment in time where it was the 5th century BC. And it was already widely accepted that the Earth is round. So that was many, many centuries ago. And I like pointing this out because, as you know, there are many people now not believing that the Earth is round, but we actually knew that for a very long time ago. But when we had first telescopes, or even before that, when we started thinking in more practical ways about the skies and the stars that we see. It was now not BC anymore, but first and second century AD. Ptolemy was an astronomer, and he wrote this book, Almagest, that was kind of a first true astronomical book, but it wasn't very fun because it was basically just pages and pages of tables of positions of different objects and stars and planets. Of course, he didn't know what they are, but he saw objects in the sky, and he mapped them and put their positions in the table so that people who have the book can look and predict where these stars are going to be in 3 months or 5 months or 6 months, which can be useful for navigation when you're on a ship, or if you're doing agriculture and you want to figure out what time of the year it is. So they knew things were moving around and changing in some cyclical way, and he just wrote things down so people can actually use this more easily. But the first time where we started thinking about how our own system works and figuring out that there is a solar system or something like that was many centuries later, in the 16th and the 17th century. Initially, Copernicus was the first person to talk about this, although he got it wrong. So he said that the universe is a heliocentric system, meaning helios is Greek for sun. So it is the universe where our sun is the center of everything, and everything else, the planets and the stars and everything else, just revolves around the sun. But at the same time, roughly, Giordano Bruno figured out something different. He said, solar system is just one of many systems. So it's not a center, it's just one of many, and we happen to be in that one. The first time we started thinking about space in a different way, in not astronomical way, because all of these, as you can see, are just about positions, movements of objects, where we are compared to other objects. Do we move? Are we not moving? Are we in the center? Are we somewhere else? But the first time we started thinking about space in a physicsy way is in the 17th century with Kepler and Newton. Newton, of course, you know, it's the man behind gravity and how it works. But Kepler also figured out that gravity is what drives the motion of celestial objects too, so that the same physics laws that we figure out work on Earth actually work in space too. So we could think about studying the space and figuring out how things move around and why they're moving around, not just writing down their positions and not really thinking about like why they're moving at all. Okay, so this is, in my opinion, the start of astrophysics in some way, even though it's still really pretty much about movement of the objects, but it's viewing the problem in a different way. And it wasn't until 2 centuries later that things started to move a lot faster. So in the 19th century, so we knew a lot more about physics. Particle physics was already a thing. We knew quite a lot about all kinds of physical processes, even high energy physics. But when it came to space, we thought that the universe is still completely static. So things are the way they are. Sure, they move a little bit because of gravity of other objects, but basically the stars will be where they are now forever. We are where we are, we're not moving anywhere, and that's it, on the large scale. So we thought the universe had no beginning, no end, everything is static, and that's it. And how we changed our opinion is because of course, Albert Einstein. Even though he also had a difficult time accepting this, his own like discovery. So in the 20th century, you've probably heard that he wrote 2 big, very important papers with special theory of relativity and general theory of relativity. So in one, he figured out that space and time are not separate things. They are connected, and they can influence one another. But in the second one, he also realized that the space, because of this connection, the space can contract and expand. And in this, and this is the only equation I'm going to show you, but I'm not going to walk through all of these things. The main point of this equation is that everything on the left describes the shape of the universe and if it changes or not. So these terms describe, let's say, the evolution of the universe, if it evolves at all. The other side describes all of the matter and all of the energy in the universe. And because these things, two things are connected, if you have, for example, perfect balance, it will be a static universe. But if you have, for example, a lot of energy and a lot of matter creating a lot of gravity, that will pull the universe in some way. So it might contract it, it might expand it, and so on. So he realized that even though possible, it would be probably very unlikely that these two terms are in perfect balance, so that the universe is perfectly still. So he artificially introduced this lambda factor, like a constant here, to like a fudge factor, to account for the inequality between the two sides and artificially make it balance. So he said, okay, maybe we don't know what this is exactly, but there is some factor that will make the universe static when we calculate perfectly, like what are the contents of the universe, so that we can balance it perfectly. And he called it cosmological term. Interestingly, as you can see, many years later, in 31, he himself realized that this was a mistake and this probably shouldn't be artificially tuned. We should just accept that the universe is not static. This term actually still exists, but it is a different kind of value now that actually correctly describes how the universe evolves. So he was kind of right putting this value here, but not right in the way he was thinking about it. So if the universe is not static, and so from the 20th century and after Einstein, we believe it's not, that means that the universe is evolving in some way. And what is actually happening is that the universe is expanding. And I will show you why we believe it's expanding. So if the universe is expanding, that means if we rewind the time, very, very long time ago, the universe was smaller and smaller, and initially it was just one point in space. So this type of theory of is, and you've absolutely heard about it, is called the Big Bang theory. Interestingly, Fred Hoyle in the 50s actually invented the name Big Bang, although this theory wasn't really existent back then. He just called the theory or group of theories trying to explain the universe as non-static. So if it's not static, it's evolving, let's call it Big Bang theory. It was like without all of the details that we know now, but it was an idea. So I'm going to, by the end of this hour, hopefully, we have time, I'm going to try to show you a couple of different puzzle pieces and evidence that we have today that actually support this theory in, like, with very precise measurements and interesting findings that really connect very well to the theory and make us really believe that this is the correct theory. So let's start with evidence number one. So if the universe is expanding, we could potentially, right, measure some objects in the universe and see if they're really moving away from us. So if they are, this is the first piece of evidence that the universe is expanding. And let's observe galaxies. They are distant objects. So if we could measure their positions and movements and see if they're going away from us or not going anywhere or going towards, we can figure out like what's going on, right? Okay, so who did this? The most important person for this finding is Edwin Hubble. You've probably heard about him. There is a very big telescope in orbit called the Hubble Space Telescope that's named after him. And he was a student at UChicago. Interestingly, he also played basketball for the UChicago team. And he was actually born in Missouri and then moved to Wheaton, Illinois in 1900s. And Wheaton is like literally right there next to Fermilab. So I didn't know this until a few years ago. So I was very surprised, and it's really cool, I think, that he lived here. After he graduated, he worked at this 100-inch telescope near LA. So he discovered that other galaxies are actually other galaxies. So before Edwin Hubble, we didn't know what they are. We called them nebulae. So we just saw that there are some like more extended blurry objects, different in some way to stars that are compact, smaller, and very bright. But we didn't know what these objects were and where they were. Were they in our galaxy or maybe somewhere else? And when he figured these are actually different objects very far away, there was a really cool article in 24 in the newspapers, New York Times, about this finding. I think this is pretty cool. I guess at that time, newspapers was the main thing to read. So how did he figure this out? He figured it out because of Henrietta Swan-Leavitt. She worked at Harvard College Observatory, and she was observing small and large Magellanic Clouds. So these two galaxies here. These galaxies are the closest galaxies to the Milky Way. Of course, she didn't know these are other galaxies at that time. They're small and irregularly shaped galaxies, but because they're really close, we can see them as very extended objects. You can see how big they are compared to the trees. So she was observing stars in these two objects. And what did she see? She saw that there is a specific type of stars that looks very weird. So majority of stars, they have some brightness, and that brightness is constant. It's just their brightness dependent on the size and temperature they have. But some stars change their brightness, and they actually oscillate in brightness like this. And this plot that we made here this is time. Unfortunately, no time axis, but this is time. Oh, okay, it's on top. So it's time in days, and the y-axis is the magnitude, which is just, let's say, brightness of a star, but astronomers like to talk about in these units. But what you can also see is that these oscillations are very regular. So the period of each oscillation is the same. The size of the jump is always the same. And so this variability is pretty constant. And for each star that she measured, she found that each star has a similar type of constant variability. Maybe the difference in magnitudes is different, but it's for that particular star, it's always going to be the same. And when she plotted a plot where she put luminosity, or again, a type of brightness measurement for stars, and the period, we saw that all of them are pretty lining up very well with just a single line. So if the star has longer periods of oscillation of brightness, that means that the peak luminosity for that star is also going to be larger. So this star here has very high brightness in the peak here, and also it's oscillating slowly. But this one has a shorter period and is not as bright. So this was a very interesting finding. But and also these stars are called Cepheid stars, which I forgot to mention. And what this means is that you can really easily, because of this property, use them as something we call standard candles. That means that if, for example, if you had a candle and you were holding a candle, right, and you were very close to me, the brightness from the candle that I would see is some specific value. But if you were moving away from me, I can calculate exactly how dimmer that same candle is going to look like. And because of that, if I measure the brightness of a candle, I can basically tell you how far away you are from me. And in a similar way, we can do the same thing with stars that are like this. So basically, what you would do is you would measure the period, look how bright it should be, and then see what you actually measure. So if I measure anything that's dimmer than this value, that means that that particular star is specific number of light years from me, right? It's distant. If it were right next to me, I would see exact value on this plot. So this is a very simple way, but actually pretty, like, I don't know, safe way of measuring distances. So because of her, Hubble knew that this law exists and that he could use Cepheid stars to measure distances. And he actually did that for these two galaxies. One is called not Triangulum or M33, and the other one is called Andromeda Galaxy. Maybe you've heard about Andromeda. That's the closest large spiral galaxy to the Milky Way. So he measured Cepheid stars in these galaxies, and when he calculated where these Cepheid stars should be, so how distant these objects are, he realized that they are 930,000 light years away. So Milky Way has the size, this was known already back then, of only 100,000 light years, so across like this. So basically, this object is more than 9 times more distant, right, than anything in our own Milky Way. So obviously, these stars have to be in different galaxies. So these nebulae are not really nebulae. They are galaxies very far away. So that is how Hubble measured distances. But distance alone doesn't mean anything as an evidence for the expansion of the universe. What we actually have to measure is, are these galaxies moving away from us or not? If they are, then there is expansion. And there is, again, a very, very simple physical law that you experience every day that we can use to measure the velocity of objects. And that is the Doppler effect. You've experienced it, as I said, every day of your life. So if you have a sound wave coming to you, so maybe from a car, if the car is static, you will hear some specific type of noise with some specific frequency. But as soon as that car starts moving towards you, right, the pitch of that noise starts becoming higher and higher, right? And that is because the sound waves are becoming kind of squished, and you're receiving sound with lower frequency, with higher frequency, so it's squished. As soon as the car passes you, these sound waves become stretched out, and you can see a lower and lower pitched frequency. So the light is also a wave. So this sound wave is one thing that we could measure, but we could also measure the same thing for light waves. And oh, I lied. This is the second formula that I'm showing you. But this formula just says the frequency for me as an observer of an object that is producing a frequency f0 changes with respect to all of these terms that are multiplying it. And these are the movement of the object producing, the movement of me as an observer. If I'm also walking, I'm adding extra velocity, right? And the speed of the sound in this case. Or if I was doing light, that would be the speed of light. So this is how I can calculate what I will hear depending on what is being produced and how we are all moving around. Okay, so how do we do that for galaxies? So for galaxies, we can measure their spectrum. Spectrum is the amount of light at different frequencies. So it's kind of a 1D version of a picture. So in blue light, I have some value, and then in green and red and yellow light, I have some different amount of light that I'm receiving, and this is called a spectrum. So we can measure something like this for all galaxies. And interestingly, when we were starting to do this, when we've made first spectrographs, we saw that there are gaps like these black lines in different locations in these spectra. These black lines are called absorption lines. So they're lines produced by atoms in galaxies that are absorbing light of specific frequency. They just absorb it, and hence we get a gap. We don't receive anything at that frequency. Depending on which atoms are contained there, because of we know exactly which gaps we should get. So for hydrogen atoms, we know what the values for like different electrons and atomic levels in these elements are. And so we know what helium, what hydrogen, what all other atoms will absorb. So basically, by looking at these lines, if the galaxy is not moving at all, we know exactly where these lines should be. But what we saw when we were starting to actually observe that we saw that these lines are actually shifted in some way, meaning the galaxy's light is being stretched out or contracted. So if I know that a static galaxy will produce a line here, if it's moving away from me, this line is going to move towards red light. So this is also called the redshift. And if for some reason the galaxy was moving towards me, this line would move more towards the blue part of the spectrum. So this was first measured by Vesta Slifer, who worked at Lowell Observatory in Arizona, which also is the observatory that discovered Pluto. So that's a fun fact. But he measured these different nebulae or different galaxies and their spectra. The spectra now looks pretty like boring compared to the nice colorful picture that I showed, but this is the same thing. It measures some light amount at different frequencies, and you can see like small gaps. The strongest ones are these two here that are from hydrogen. And these lines on top and bottom just mark where the lines were found. So as you can see, the same two lines for Virgo are here. Then for the next one, Ursa Major, it's slightly to the right, so slightly towards red. And then for this one, it's even more towards red, and so on and so on. So all of them and everything that he observed was basically shifted more or less towards the red side of the spectrum. And hence, that is why he called this effect the redshift effect. So this is how we know, because of redshift, that these galaxies are also moving away from us. So like, let's put these two puzzle pieces together and go back to Hubble, basically. So he measured both of these things. So he measured positions, like distances of galaxies, and he measured also their redshifts so that he can calculate how quickly they're moving away from him. And so he got a plot like this one. So for each galaxy, he puts a dot in the plot depending on where it is and what the velocity he got. And he saw that, okay, there is some scatter, but basically he could draw a line through these galaxies. So he basically could write an equation like this, where he said, okay, the velocity of the galaxy depends on some constant times the distance. So if I measure the distance, I will pretty much know the velocity if I know this constant. And today, of course, we call this constant the Hubble constant. So the more distant the object is from us, the faster it's moving away from us. So that was something that he discovered from like making this plot. But there is one very important thing to note here, is that this doesn't mean that the universe is heliocentric and that everything is moving away from us. We can think of the universe as a loaf of bread with raisins, where every single raisin, as the bread rises, every single raisin will see the same effect. So all of the other raisins are moving away from you. And the more distant the raisin, it looks as if it's moving faster. So there is no special raisin, and the sun and us are not special. It's not in the center. Everything is expanding. So if the whole space is expanding, every object in it sees the same thing. I should speed up. So today we actually have an even better evidence of this effect by measuring a lot brighter objects called supernovae. These are exploding stars. And because they're a lot brighter than regular stars, they happen when these specific type of explosions. They always explode with the same brightness. So again, can be used as standard candles. So that's the most important part. It has to be always the same explosion size. And they happen when you have a system like these two stars, where one is kind of snatching the gas from the other. And at some point, it's always the same point, it becomes like a critical mass and it explodes. And these three people here measured distances to these exploding stars using the same principle, right? So you measure how bright it is, the same as like the Cepheid stars. And they realized when they plotted them here, this plot kind of shows you where these explosions should be. They should be, if the space is decelerating, they should be in the red part of the plot, if it's accelerating in the blue part, and if it's static on the line. And when you look, it's slightly shifted towards blue. And because of that, there was an extra evidence that even on very high distances, the universe is still. And they even won a Nobel Prize very recently for this story. Okay. The end of evidence one. Evidence two is slightly shorter because they're just one single piece of the story that I have to tell. So the other one is observation of the cosmic microwave background radiation. And I will try to explain what this is. So to explain what this cosmic microwave background radiation is, let's try and quickly describe what happened after the Big Bang in like some major steps that happened. So first of all, many of these steps are all going to happen within 1 second after the Big Bang. So right after the Big Bang, the universe was immensely dense and warm and chaotic. It was just basically one huge fireball in some way. But it's quickly expanded and cooled down a little bit. We call this period inflation. It is, as you can see still here, like very, very tiny part of a first second. Still within 1 second, it cooled down even further so that the forces can decouple from this chaos so that gravity becomes a force, but then also strong force, weak force that govern how nuclei and atoms work, and also electromagnetic that you can see in your everyday life. And since these became a thing, after a couple of more parts of the second, when it further cooled down, the first building blocks of atoms, so the smallest types of particles appeared, like quark, electrons, protons, neutrinos. So things that are simpler and things that are also building blocks for more complicated, larger nuclei and atoms. Yeah, so this is, again, within 1 second. And now we're first time out of this first second. So in the first 4 seconds, this is all that existed. But at around 4 seconds mark, it was cool enough for first neutrons and protons and electrons to exist. They were still separate particles. They couldn't really do anything together because it was too hot, but they existed. And then in the first 2 to 20 minutes after the Big Bang, first nuclei were formed. So these protons and neutrons were able, it was cool enough for them to actually bind together and make nuclei. They were still not atoms. The electrons were separate, but the nuclei of first smallest, simplest elements were formed. And those are only these elements. So hydrogen, heavy hydrogen, are called deuterium, helium, and just a tiny pinch of lithium. And that's it, nothing else. So, that happened in the first 20 minutes. And then nothing changed for 380,000 years. You just have these neutrons and protons and nuclei flying around, nothing happening. So it took universe this many years to cool down further enough for these nuclei to finally capture all of the electrons and become atoms. So now, because things are all binding atoms, the light is finally free to move through the space as it wants. So it's not bumping into electrons and protons and neutrons all the time, disappearing, being absorbed all the time. So basically, this is the time in the universe's history, the first time where the light is free and the first light that we could potentially observe. So this is the light that today we call cosmic microwave background, and I will show you why. But I also want to say that first stars and galaxies now have formed 300 million years after the Big Bang. So this was in 100,000 years. This is millions of years. And solar system forms around 9 billion years after the Big Bang. And today we are at 13.77 billion years. So this is the present day, and this is the age of our universe. So let's go back to this first slide that I was mentioning. So the universe at that time was 3,000 kelvins hot. Kelvin is a unit of measurement for temperature, just like Fahrenheit or Celsius. It's just something that in the sciences we like to use. You can convert it very simply to Celsius with this equation, and slightly less simply to Fahrenheit, but it's just a measure of temperature. So it was pretty hot. 3,000 kelvins is a lot. So how do we measure this first light? When did this happen, and how did we figure out that we're doing that? So that happened in New Jersey in the 60s. It was done by Robert Wilson and Andro Penzias. They had this very weird radio antenna. So they wanted to observe the sky in radio waves. Radio waves are the waves with longest wavelengths, the same waves that we use for radio, so to listen to music. But what they saw is that, sure, they can maybe observe some objects, but there is some background noise everywhere. Wherever they turn, it's the same background noise. And that background noise was calculated to be of something that has 2.7 Kelvin, so very cold. And they didn't really know what this is at that time. They even thought that it might be pigeons creating the noise because they were like nesting inside of the antenna. They had to clean everything out. But yeah, the noise still remained. And so they didn't really figure out what it was, but they were sure that they're observing it. The person who actually did figure this out is a theorist, Robert Dicke. He worked at Princeton, and he said, okay, if there was a Big Bang, and if we had this first light at very high temperatures form at this particular time that I mentioned, it should cool down by now. And it should now look like a very low level background radiation of very low temperatures, exactly what they were observing. So actually some part of that light is actually in old, I don't know if you have ever seen this in person, but this is how the old TVs look like. So if there was no channel on it, you could see like this noise. Majority of this noise is nothing special, but some part of this noise actually is that light. So that's kind of fun. And he even won a Nobel Prize in '87 for this discovery. So how do we know it's a 2.7 Kelvin signal? So how do we know this is that temperature? So when Andro and Penzias measured 2.7 kelvins, their whole sky looked basically like this. So everything was the same. Let's say that this green shows 2.7 kelvins. The only thing that was slightly brighter is on the horizontal line is the Milky Way, our own galaxy. And if you plot how the signal looks like, it's like this. This is something that we call a black body radiation signal. So there is an exact formula that tells you if you have a specific temperature, how should this curve look for you? And basically, if you measure a curve like this, you can really, really precisely calculate the temperature of an object. And so this is what they did. And when they measured this very precisely, which they could at that time, they figured out this is 2.725 Kelvin. So after that, we wanted to figure out, is it really so smooth? So we launched a bunch of telescopes in orbit to get better resolution. The first one was COBE, and you can see that it saw, again, the red is the Milky Way, the brightest point, but it saw some fluctuations, and these fluctuations were at like 10,000 per 1 Kelvin, so that rate. Then we launched another one, WMAP, and we improved the resolution of the temperature that we were measuring by 1 point. And you can see now that the fluctuations are even smaller. But then we launched another telescope, which is Planck, and it saw even smaller fluctuations. These fluctuations are really, really, really small. As you can see here, they are actually 1 part in 100,000. So if the Earth, for example, was as flat as this background radiation, the highest mountain would be just 300 feet tall, so like 100 meters. So these fluctuations are absurdly tiny, but we can still measure them very precisely. So now we know that we actually indeed are observing this first light, and the fact that it's not very smooth actually reflects the fact that initially these atoms were not perfectly uniformly distributed. They were just randomly distributed in space, and there are small fluctuations. So these first photons had, in some places, more space to traverse the space. In some others, there were other atoms that are blocking them, and so on. And hence, we can see these very small fluctuations. Overall, this is tiny, but still, this existed, this small fluctuation. Okay, so the third part of the evidence is very brief. Since we started 5 minutes late, I'm just going to do the third one, and then we're going to make a break. The third part is the observation of first elements in the universe. So if you remember, I said that hydrogen, deuterium, helium, and lithium were made in the first 20 minutes. So can we find very old objects and measure the amount of these atoms to see if they match what the theory says? So yeah, as I said, now we're thinking about this first 20 minutes period. The person to measure that and figure that out is, again, a professor from the University of Chicago, David Schramm. So we knew that we had a theory, right? We knew how particle physics works, so we could figure out, depending on the environment, so how dense, how hot the universe was, how many elements we could form of different types. And so we had a plot like this with these curves from theory. So this is how many baryons to photons, so how many nuclei compared to like free photons you had in the universe, and how much of like hydrogen, deuterium, helium, and lithium you can make. And so these curves show you what the theory says. If our observations match this, then this means the theory is correct, right? We knew what the temperature and this baryon to photon ratio is because of the CMB observations, cosmic microwave background that I said before. So we knew exactly the temperature, and based on that, we knew what this ratio should be. So basically, we should observe things that are around the intersection of these curves with this vertical line. And we decided to observe extremely old stars. Old stars, the first stars that formed in space, they only had that material to form an object, right? So if the amount of hydrogen, helium, and lithium in these stars is the same that we predict, those values are pretty much what was there in the early universe. And these yellow boxes are what we measure. So this box is big because the error bar for this measurement is big. But for example, for the blue line, it's very precise. This one is also correct. I don't know why they didn't plot it in this example, but it also is here. So for majority of elements, we were pretty spot on. The only problem currently is the lithium, which is here. not really where it's supposed to be, but we believe, and this is called today the lithium problem. This is something that I was studying during my PhD. But we believe that this is just because the mechanisms for producing and destroying lithium after the Big Bang are more complicated than what we think. And so something happened to the lithium that we still don't fully understand, and this is why this is not matching. So hopefully we'll figure this out and be completely sure about our theory. But one thing that is interesting that I just want to point out before we make a break is that everything in the universe so far that we know actually destroys lithium. So all of the processes in stars and in space, everything destroys lithium. So all of the lithium that you have in all of your batteries, in cars, in phones, everything, all of the lithium is made in the Big Bang. So that's kind of fun to think. So to think about, because that happened, billions of years ago, and now we have enough of it on Earth to make all of the batteries. And you have to remember that this, as I said, it was made just like a tiny pinch of lithium compared to all of the other elements. So that tiny pinch of lithium in space is actually enough for all of our batteries. So yeah, so with all of this evidence, we now believe the Big Bang theory. We know that the universe evolved from this Big Bang event, that things were not very uniform. They were slightly, off, more dense or less dense in different places. And then with gravity and time, these irregularities evolved to form all of the planets and all of the galaxies and clusters and so on. So everything that we see today, just because things were not perfectly even. So those tiny, tiny fluctuations in the CMB, that is what caused the evolution and formation of everything in the universe. Of course, because of the gravity. So here, I will stop. And then in the next part, I'm going to show you how we are using machine learning to actually study all of these objects. Okay?
All right. How about we do some questions? Hopefully some questions stirring around in your brain, maybe. Second. Also look at Zoom. So you were giving the example. I always think it's hard to think of cosmology, or at least it's like the expansion of space. So you give the analogy of like raisins in a piece of bread. I've also heard of analogy of like, it's weird. I don't know if you guys got onto that. There's an idea of like space itself is actually expanding. So it's like, usually when we think about distances, we say like, the distance from this corner to this corner is of this table, or the distance from here to Chicago is some fixed distance. But when we're talking about the expansion of space, you're actually talking about, so if you imagine like a grid, usually in cosmology class, you draw like a grid, something like, sorry, people on Zoom, maybe you can see it.
If you stand here, they will see it. Yes, there, somewhere like that.
And there's 2 points on the grid. So there's some distance, between these 2 points. And that's like, we call it like a physical distance, right? But then the expansion of space is saying that, actually, the grid is getting bigger. So there's some characteristic, it's usually denoted by A in cosmology. So when we're saying that space is expanding, we're saying like the actual physical space, itself is expanding. And so when you're actually measuring a distance, you have to think about, the units of the grid as well as, the physical space. So it's kind of hard to wrap your head around. I don't know. Any questions?
If matter can't be created or destroyed, what's filling the space?
So in some way, so we don't know what happened before the Big Bang. So we're like not trying to figure that out. But at that point, things were, for us at least today, created. So matter and energy are kind of different forms of the same thing. So you can like convert, as you know, matter into energy by like, for example, destroying atoms, which we do in bombs. So things can convert from one to another, but that's it. Like what happened after the Big Bang, the amount of things, of matter and energy that we have in the universe, that now is constant because we can't create new matter or new energy, but we can convert from one to the other because they're kind of, yeah, different sides of the same coin in some way. Go ahead. Do we need a mic for his question?
Yeah, so there's one question from Zoom, and then
okay.
I'll get yours.
Okay.
So will the universe expand forever? Are we moving towards something in particular, or is there like a specific endpoint of the expansion that we can tell?
Yeah. So from what we have observed, so all of the evidence now is that it's going to be expanding forever, and it's expanding faster and faster. So things are just going to be more and more distant, and many billions of years later, you will just not see anything because the space is going to be expanding faster than the speed of light. So anything that's anywhere will not be able to reach you ever. So, I mean, that's in absurdly long distant future, but that's what we think will happen currently based on the measurements, because we see that the universe is just expanding faster and faster. So yeah, that's probably our fate.
Why is it that lithium is only being destroyed?
It's just because of the form of the atom. It's pretty, the number of neutrons, protons, and electrons, and all of the chemistry, like in stars and other places, it's not very stable. So it just, all of the things that we know happen in stars and later on in gas and in galaxies, we see that all of these like reactions actually can just destroy it and make it into smaller building blocks. For example, like destroy lithium and make helium plus some rest. So it's just that it's not very stable. So in the periodic system of elements that we have today, you have elements that are more stable and less stable depending on like how many electrons they have and so on. And what I didn't say, which is also very interesting, is that all of these elements that were made in Big Bang, there's like 3 elements, that's it, but all of the rest, so all of the copper and iron and all of the other stuff, these things were made in stars. So the fusion of atoms in stars forms everything from lithium to iron. That's it. And then again, nothing heavier. All of the heavier stuff like uranium or even more regular stuff, but that's just heavier than iron, is only made in explosions of stars, so supernovae. So when stars explode, there is more energy, so you can actually create these heavier things. But without supernovae, we would not have anything higher than iron, for example. That's kind of a fun thing to think about.
All right, last question, then we'll go to break.
I don't know exactly how to phrase this, but how do we know what happened in the Big Bang and now?
Again, because of how we understand particle physics and how like these simple like gravity, electromagnetic, nuclear forces work. We understand how they should work and how they should influence particles at different temperatures, pressures, and so on. So by kind of observing what we can and a lot of work from theorists, we kind of figured out how, based on the environment in the universe, how these things should evolve, and also how they should guide the formation of particles and what they can do and what they cannot do. So basically, just a lot of work from theorists, and then experimentalists and observers trying to find specific things that we can observe that actually works with the theory.
And we're gonna have a panel afterwards. I mean, it's fine. We'll see. Go to 11. We'll see how it goes.
Okay.
I mean, trying to do that 11. If you run over, it's fine.
Okay. Okay, I'll try not to. I'll try. Okay, so slightly shifting gears, but not really. It's more about some like newer techniques now. And I don't know. I'm going to try to explain what AI is so that you understand what I'm talking about, but then I'll show you like some examples. And this is just like, again, a very small sample of things that we're doing today with AI. But yeah, how many of you, question, I guess, how many of you used AI so far? Okay, that's pretty good. But also, people who did not raise their arms are wrong, because you did. Everybody uses it now. Like, even if you don't know you're using it, you have it in your phones so that it can recognize your face and put a nice like filter on top, or like maybe a sunglasses or something. It's in the phones. It's on any of the platforms that your preferred choice for, like streaming platform for movies and TV shows. It watches what you like and recommends new things based on what you like and what people who like the same things that you like. Facebook, Instagram, Twitter, everything, all of the ads that pop up based on what you say or do or look at, that's all AI looking at like the pieces of evidence about you and what you might like to look at next. So I don't know if this is good or bad, but you have all been using AI, maybe not building it, but using it definitely. So, but again, like for science, it's slightly different. And I want to introduce like why AI is even a thing in science today, why today, why not 50 years ago or whatever. So the history of astronomy and astrophysics evolved as our telescopes evolved, because we had different amounts of data and different quality of data over time. So we initially built, our first telescopes, and this is an actual telescope from an old observatory in my hometown in Belgrade. Of course, we had many more like this and similar ones, but then at some point we were able to launch things into space so that we can see in much better quality, more distant, more fainter objects, because we don't have the atmosphere to interfere with the light. But the telescopes on Earth were still and are still a thing. We are building a lot of them. But we figured out that we could also make arrays of telescopes like this one here, to kind of be a substitute for one ginormous huge telescope. So all of these telescopes kind of observe things in together as one and give you a very precise, very high resolution picture that a single dish would not be able to. And because of all of these telescopes, we have observations of the entire sky at many different wavelengths. So these are some examples. This one, for example, is our sky in gamma rays. So the highest energy photons with lowest, smallest wavelengths. And in all of these are some other ones. You can see that our Milky Way on the horizontal line is always the brightest, which makes sense. It is the closest thing to us, as observers, our own galaxy, but you can see different things up or down from the Milky Way too. But as astronomy evolved, computing also evolved. So in the 60s, you had first computers, and we call this kind of a mainframe era, where you had a huge computer that wasn't very powerful by today's standards at all. It filled the entire rooms, weighed tons. And for example, you had a university, they would have this computer, and all of the students, all of the professors, everyone in that university could use that single computer for their tasks. Of course, we couldn't do very much with that, but that's kind of what the 60s looked like. But just many years later, the technology changed so that we could cram this into smaller personal computers or PCs, so that everyone could buy one and have one at home. So it was one computer, one user, or a family, or something like that. In 2000s, we have the mobility era, where this is further reduced, and also it's, again, even cheaper to produce it, so that you can buy multiple computers in your phone, in your laptop, tablet, or whatever. So every individual now has more than one computer. And finally, today we say that each person has maybe even hundreds of computers at their disposal. So because not only you have the obvious choices like the phone and tablet or laptop, you have computers in dishwashers and washing machines, in your cars, but you also have more powerful computers owned by companies like Google, Microsoft, and so on that you can either for free or for some fee use if you need something that's more powerful than what you own. And this is what scientists use. They also, I mean, we use our own powerful computers, but you can also use, the industry powerful computers or people or other universities and so on. So basically, because of these two things that we have today, very powerful computers, but also insanely large data sets, this is what kind of brought us to the AI era and the fact that we actually need something like AI to do science. But before we again move on to like how these type of algorithms work, I want to distinguish between these three terms because people really use them interchangeably all the time, everywhere, but they're not really exactly the same. So I just wanted you to kind of learn what they actually mean. So artificial intelligence algorithms, they are the biggest group of algorithms. They include any algorithm that mimics some kind of human behavior. So even if you hard code that behavior, for example, if you see number 1, do this thing. If you see number 2, do this other task. So it can be hard coded, nothing fancy or special about it, but it is mimicking something that you want to do or you would have done if you were doing things manually. But there is a subset of algorithms that we call machine learning algorithms that are a subset of artificial intelligence. These algorithms, again, mimic human behavior, but the way they are doing it is completely different than what we had before. Meaning these algorithms actually learn how to behave from examples, just like human babies do, right? So you show this algorithm a bunch of examples saying, I don't know, this image of a puppy is connected to a word puppy, and this kind of image of a kitten is connected to a word kitten, so that it learns how to connect these terms, and from that maybe be able to recognize a new type of image. So that is the same thing you would do with a baby, right? You would show it a bunch of cats and be like, cat, 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 and eventually it says a cat when it sees a new. The small subset of that is called deep learning. And it is the same kind of principle, so it still learns from examples, but the type of algorithm is slightly more complicated and usually involves something called a neural network. You could do a similar thing without neural networks, but then it would be machine learning. So a small fun history of how AI came to be is I also learned this very recently from a very cool book that I have in my slides, I think, as a recommendation at the end, if people are interested. So in 1943, these two guys, McCulloch and Peets, were talking. And interestingly, so McCulloch was like a neuroscience professor, again, at U Chicago. And Peets at that time was weirdly a high school dropout, but he was really good in math. So later on, he would, continue being in like the math computer science field. But at that time, he was just kind of around. And by a chance, and his friend that he was studying at the University of Chicago, these two met, and they talked about the brain and about the neuron. So one was looking at it from like a biological standpoint, and the other person was looking at the neuron from like more a math computer science perspective. So neuron look in a brain, so brain cell looks like this. It has the main part of the cell and these dendrites that are connecting it to other cells. It also has this axion and synapses, again, to forward some electrical signal that is formed here, and through synapses connected to the next cell. But even though you can do very complicated things with your brain, where you have billions and billions of these connecting and moving the electrical signals back and forth, if you look at a single cell, it's pretty simple. You can think about it in a very mathematical term, and they actually wrote a paper about it. It wasn't very highly cited, but it exists, and it's kind of fun to find it and look at it. But so you can think about it in a simple term. So instead of electrical current, let's say that we have some values, some numbers that go as inputs to our neural, like fake brain cell. It does some kind of process with these values. So there is a function that changes this information in some way and combines it. And then this output Y is forwarded to the next one. And that's it. It's quite simple, right? And even though, again, this single fake cell cannot do much, maybe just like brain, we could connect a bunch of them and actually do more complex things. And just kind of in the next decade, people started thinking about this and getting more and more excited about the possibilities of artificial intelligence and these artificial neurons. And they even had a conference in Dartmouth where in '56 they established the research field as the field of artificial intelligence, and the name was like, officially made. But they couldn't really do that much because computing wasn't very powerful at that time. They didn't really figure everything out yet. But there was a lot of hype, a lot of funding, and then no funding, and then funding again, and no funding. So it's very like oscillating the whole field. But the fun part that happened, it was in the 80s, is the creation of Fukushima's neocognitron, this algorithm that tries to dissect the shape and understand it. So this kind of shape, we can kind of cut it into horizontal, vertical, and diagonal lines, and then we can combine our knowledge of these type of lines into more complex parts of the shape. And then these are combined into more complicated parts until you can reconstruct the whole shape. This was still not any kind of machine learning or anything like that, but this kind of logic where we could maybe try to figure out simpler parts of a shape to understand the whole shape is really was a kind of a changing point. An important part where this same kind of principle was actually done with these neural networks that I'll explain later was actually in '88 by Jan LeCun, who made something called a convolutional neural network. And he is very big name in AI still, and he will be until, as long as he lives. He made a CNN, so an AI algorithm that can understand digits, written digits and numbers. So that, for example, and like printed digits, of course, so that you can scan checks and automatically get your like account number out, and you can put that into a machine and just do that quickly. And it's still being used in those machines. So like the checks, and the majority of checks in the US are scanned this way in all of the ATMs and in the bank and everywhere, which speeds things up crazily, like a bound. So the final step in this evolution, I think the very important part was in 2012, a thing done by Alex Kryzhevsky, who was a PhD student at that time. So he was studying computer science, and he was learning how to program on GPUs. So regular programming, nothing AI related. So GPUs are like graphical cards in computers that run your video games. They're a lot more powerful than CPU. So all of the gaming engines and all of the programming regarding any kind of visual stuff for your computers has to be done in a specific way for these GPUs. And of course, he knew about AI because of Jan LeCun and all of the things that were done before. And so he realized, okay, maybe I could rewrite these algorithms to run on GPU so that I can actually use this for something more complicated than digits. And so he did that in his dorm room, in his room. And he entered a competition that already existed for years before that called ImageNet competition, which is a competition where you write any kind of algorithm, it doesn't matter what it is. The goal of the competition is to try to classify images in this huge data set. These images have hundreds of classes, like birds, cars, buses, whatever, things like regular things like that. And he made a neural network that he trained on this data set on GPU for like, I think 1 or 2 days straight, nonstop. It was like 1,000,000 degrees in his room because of the computer was like generating so much heat. But he entered this competition and he was so much better than anyone else. It was like, I think like 10, 20% accuracy better than anyone else. He instantly became like super famous. But also he showed everyone that by doing things on GPUs, you can actually use AI for many different useful things. Things where you have larger data sets, where you have more complicated data sets, and you can still do it in a reasonable amount of time. You don't need years to train a program or something like that. So because of this event, I think, and I mean, that was really recently, all of the things that happened later on are happening, and everything is in the AI field, honestly, is moving extremely fast, much faster than any other science. So it's kind of crazy, of course, because more people are doing things with AI because of all the companies and everything, because of all of the useful other like non-sciencey applications. But why is AI used, and why is it important for astrophysics or for cosmology? Well, because with GPUs now, we can create models that can look at thousands and millions of images or any kind of type of data that we have of astrophysical objects. That means that we can build models based on the data itself. We don't need to write things down explicitly in equations all the time as we did before. So before, when we did everything with equations that we had to calculate manually or with some regular algorithm, we had to make all kinds of approximations. So a galaxy was usually approximated as a sphere or a disk or something like that. And it's pretty obvious that all of this is not correct or good enough. So if you want to study anything small scale or something like that, you run into problems when you do this sort of approximations. So now with AI, we don't really have to do this anymore. So it accelerates research. It allows us to make models based on the data and not approximated versions of our data. It helps us reduce the space of the problem. So if your galaxy is very complicated, it helps us figure out what is important. And also helps us with unexpected discoveries because it can swift through billions of images and tell you if a galaxy is normal or a weird one that it hasn't seen it from these many examples. So like all of these things are very beneficial for us. But so how does it work? How does like these like neural networks that I mentioned work? So again, they work by combining these fake neurons, or sometimes you will see them being called perceptrons. They're all the same thing. It's basically, as I said before, you have some inputs, X. Usually you have some weights. This is actually what the neural network is trying to learn. So what is the weight to multiply each number with? This is what is training a neural network is actually means, finding these weights. When you find them, you sum them up. They go through some specific activation function to add extra changes and nonlinearities to your outputs. This is what actually allows it to learn complicated things. And then that sort of number is forwarded to the next neuron. So those are the things that you have to do. You have inputs, you have weights, you do a sum, and you forward the sum through an activation function, maybe a step function like this or something like that, to change it slightly, and then you send it to the next one. So you can have a simple algorithm where you have inputs, one layer of, for example, 3 or 4 or whatever, 100 neurons, and they all, so there is just one layer of these, and they all output a number or a set of numbers that you care about, or a class, like dog and cat. So that's it. But you can also, of course, combine them into more complicated deep neural networks, meaning there are more layers, hidden layers of these neurons. And this is just, again, a simple form of a deep neural net, you can really go crazy by the shape and size and weird kind of layers. And so these are, of course, a lot more powerful. They can work with more complicated data sets or types of data sets. And yeah, so this is basically, in many cases, this is what we would use. So for these deep learning tasks with deep neural networks, if this is an example with images, I work very often with images, especially because I'm an astrophysicist, but some astrophysicists don't work with images. Of course, they work with tabular data or with spectra or time series or whatever. But let's, like, for now, focus on images, although this applies pretty much to many other types of data too. So 3 types of tasks that you can do with images is classification. So classifying this whole image as a puppy image. Detection, meaning you want your neural network to draw a bounding box around each puppy in the image. Or the most complicated is segmentation, where you want exact boundaries of the object, or in this case, a puppy, in the image. That means that the algorithm needs to actually classify each pixel in the image so that it knows exactly which pixel belongs to the dog, which one is the stick, and which one is the background. So these are the 3 types of algorithms. All of those, when we're talking about images, are done with convolutional neural networks. And if you remember, I mentioned them with Jan LeCun, who made them to scan checks. So these are also images, right? So that you can recognize digits in checks. So there are 3 parts of a network, or of the process of training one. You have examples of images. For example, if we're doing classification, let's do a simplest thing. We want to classify images. I have to send a bunch of examples of images paired with correct labels to the algorithm so that it learns how to connect labels to images. This is a convolutional neural network, and hopefully, if it's trained, it outputs a class that is correct when it sees a new image. So let's say that my image is a galaxy image. So what do? I first have these 2D layers that are called convolutional layers with some filters that scan the image and try to extract useful information. And so these might find like horizontal lines or things that are horizontally aligned or vertically or patchy or things like that. And then as we go deeper, the network combines this information into, again, more complicated ways of seeing these patterns in the image. And somehow at the end, as you can see, we always, with each layer, we reduce the size so that this layer represents this image in some way, but the size of it is smaller. And we're kind of trying to condense this information into smaller and smaller sized shapes so that we can finally squish it into a 1D vector. So 1D line of numbers that actually in some way represents this galaxy. Then we can use this in like regular dense layers that are just those neurons that I was showing connected to one another that actually use this information to learn how to connect the image with a class and then output some numbers. For example, if my data set contains 3 classes, stars, galaxies, and nebulae, hopefully the network will output 3 numbers. And once it's trained, hopefully the largest number is going to be for the correct class. So that I see these outputs and I say, okay, the network thinks that this is a galaxy image because that's the highest number that was outputted. Of course, initially before the training has converged, these will be very random. So again, 3 parts: feature extraction, so finding clues in 2D, using the clues to learn the mapping between images and classes, and outputting the probability of things being different classes. I wanted to point out how these filters work, because it sounds magic, like magic, but it's not really. So you can think about an image as a matrix of pixel values, so a 2D values of red, green, and blue pixels, and let's say that these are like zeros and ones. these filters are just smaller matrices with some ordering of zeros and ones that slides across your image, multiplies with these values, and gives you some numbers out. So that if 1 multiplies with 1, for example, you'll have a number, but if there is a 0, it doesn't. So that in that way, it picks up on things that are similarly shaped as this filter. And so you basically sum the image up into a smaller shaped matrix that basically represents the same type of information. Let me show you how that actually looks so you can like understand what I'm talking about. So like this is an image, some pixel values are there. These are different filters, you can see them here. They all slide across, and every time they give you a slightly different version of this image. So it enhances the things that are similar to it and ignores the things that are not, right? So after that, we can reduce the size of these and redo this again and again and again. And with that, we kind of do this feature extraction through these like consecutive layers that I was mentioning. Okay. Let me show you how, again, an example of how the whole network would look like. So these are the famous digits that I was talking about. So the first layer, when these images are like from different filters. The first layer sees these numbers highlighted in a different way depending on the filter. As I said, when we go from layer 1 to layer 2, there is one operation that is called pooling that reduces the size of these 2D feature maps by maybe picking 4 by 4 part of the image and saying, okay, give me just the mean value of these 4 or max value or min value. And that way we like reduce the size. So things become weirder looking, but they are the same thing. So basically you encode the same information in a smaller size shape, so that for us as humans, this like doesn't look like much, but to the algorithm, it's the same kind of information, but just kind of squished to a smaller size. And then finally, you go to dense layers that are just 1D layers. There's some numbers in there. They change for different numbers. And then the output layer, hopefully the highest number that is outputted is the correct one. Like for 7, you get a 7 highlighted and so on. But this is the simplest thing. Of course, you can do many other more complicated things with AI algorithms, from like things like finding out if it's a puppy or a kitten to like actually making a robot walk and dance and do all of these interesting things. So all of this is different type of AI algorithms. So they can be a lot more complicated than what I'm talking about today, but you can then do all these crazy things with them. In astronomy, there like the number of papers with some kind of AI or machine learning in the title basically just skyrocketed as this became more like easily made and usable, and you can train them more easily on your computers. And in astronomy, they're kind of used for either classifying or detecting objects in images or other types of data. They're helping us with these complex simulations to speed them up, so that maybe you substitute a part of the exact simulation with an AI algorithm. They're helping us schedule observations, because scheduling is extremely hard, because everybody wants to observe, and you have to fit everyone in some way so that it's the most efficient, which is not easy at all. But also, as I said, for robots, so any kind of automation from like rovers on Mars to running experiments at Fermilab or running any kind of machinery. I'm going to focus on the first part because we don't have time to go through everything, but yeah, this is insanely large field. So let me show you 2 examples for classification, things that are I was involved in, I think both of them. First one is detecting low surface brightness galaxies, or LSBGs. These galaxies are extremely, extremely faint. And actually, we were able to observe them for the first time very recently, just with like the newest telescopes that we have. And this is because they're actually fainter than the night sky. So if you don't have a good enough telescope and don't observe for long enough, you actually don't see them at all. But these are the galaxies. You see, they're very, like, not fun, I guess. They're not fun looking, but they're super important because they're the most numerous type of galaxy in the whole universe. So they are small, very light, and they're everywhere. But they're super important for us to study because they can tell us more about the formation of the whole group of galaxies, or we call that galaxy clusters, and how all of the matter that we see and don't see in this cluster actually governs the evolution and formation of galaxies. What this means, we have to use them to figure out how much matter and what kind of matter there is, meaning visible and dark matter. So this is something that I was doing with a grad student from UChicago and a scientist, Alex Wagner, that's also at Fermilab, but also in UChicago. And we were trying to automate finding these objects from dark energy survey observations. So initially, Dimitrios had to swift manually through all of the images to make a catalog. That meant hundreds of thousands of images of blobs like this. And you can see that this is very much not a fun thing to do. And the more data we have, we will need more and more graduate students to swift through millions of images. This is just not feasible. You would need an army of students. So obviously, we want to automate this, right? What ended up being happening with this catalog that he was looking at is that he had like 400,000 candidates that he found from the data. But when he was actually looking at them, he found only around 40,000 LSBGs, so only 10%. So he had to look through 100,000 images. That is crazy. This is because the algorithms that were automatically extracting this were also finding these weird artifacts and like faint blobby things that maybe look like a galaxy, but when you look at it, it's more than obvious that this is not a faint LSBG. So once the first catalog was actually made, so that was a lot of hard work, we could train an algorithm that can classify LSBGs that we found and artifacts so that we can, in later stages, do this much better and much faster. And so the algorithm then learned how galaxies look like. So this is after the model was trained. You can like plot which pixels are the important pixels for the model. So for galaxies, you can see that it always highlights the galaxy, understands where to look, and this is the important object in this image, not, for example, this thing on the side or this thing here. And for the artifacts, it also finds these blobby things that are most important. And to the model, it's obvious that these two classes are different. Hence, it can classify all of the objects very easily. This is a kind of side thing that I wanted to mention because I mentioned dark matter when I was talking about LSBGs. So I just want to kind of highlight what it is and what we know and why we even have a term dark matter today. So for that, I have to talk just briefly about Vera Rubin. But actually, before I talk about Vera Rubin, I have to talk about Fritz Zwicky, who was Swiss astronomer, I think. Yeah, Swiss astronomer. He was observing galaxies in the Coma cluster. So this is a cluster of galaxies that are grouped together by gravity. So they kind of exist as an entity. And he was looking at how fast they're moving and rotating around one another. And he saw that, yes, that these are rotating way too fast. And they should kind of blow away from one another if they're moving that fast, but something is keeping them there. And this is because there probably is more mass in this object that we don't see, and he called that dark matter. This matter is adding extra gravity so that it allows galaxies to rotate really fast without actually pulling away from one another. So he called that dunkle materie, which means just dark matter, and hence this is kind of how the term was invented. So in a similar way, Vera Rubin did a similar type of observation, but she was not observing galaxies individually. She was observing stars in other galaxies. And so she observed stars in rotating spiral galaxies and measured their velocities. And she also saw the same effect. So stars that are very far away, like from the center, they're moving much faster than what you think they should be moving. This is kind of the curve that she was expecting, but this is what she was measuring. So obviously, these must be, something must be holding them there. So there must be extra gravity holding them there. Otherwise, like this would happen to all of the stars in the galaxy, right? So again, not only there is something that we don't see in the clusters holding the galaxies together, there is something around every galaxy holding the stars together. And what we know today is that actually only 5% of the matter that we see of regular matter is what we have in the universe. 25% of the things that we have in the universe of some kind of matter and atoms are actually part of dark matter that we don't understand and don't see, and trying to figure out what it actually is. And then the majority of 75 or 70% of everything else is dark energy, meaning the force that's pulling the universe to expand. So this is kind of what we think is the structure of matter and energy in the universe today. So the end of small digression. The second example about classification that I wanted to talk about is, again, about galaxies, but a slightly different type of galaxy. So these are galaxies that are gravitationally lensed. So their light is bent in some way, so they look very weird. So this happens when, for example, if you were here as observers on Earth, and we have a very distant galaxy here, but we have a very massive object in between, like a cluster of galaxies. The gravity of this object, it can also be a single galaxy if it's massive enough. The gravity of this object bends the space-time around itself, so the light rays are also traveling through this bent space and actually curve so that you can actually see them. If, for example, this light ray was just going through a normal, not bent space, it would just miss us completely. But because of the massive object, it bends and we can see it. But this also means that the shape of this galaxy is going to be very weird and bent also. So this is really cool because it allows us, it acts as a magnifying glass. It allows us to see very distant objects that would otherwise be too faint for us to see. So we really like to find them, but they're also going to be kind of messed up. So this is kind of how a very nice lens looks like. So you have a massive galaxy in front, and this blue arc is a distorted background galaxy. They can look way less pretty than this with like just some tiny arcs or blobs here and there, but this is a very good example of one. Again, we want to find them, but compared to regular non-lens galaxies, they're very rare. So even now we have like, let's say around 1,000-ish good observations of these galaxies. But we could automate this and probably find more easily without needing people to actually look through all of the data by training an algorithm on examples of lenses that we do have, or we can simulate, so make fake lenses. We know how to do this very well. And non-lens images. So these don't look very pretty because they're trying to simulate dark energy survey, which is a ground-based telescope. So things don't look as pretty as the previous image. But people have done this. You train an algorithm on these two classes, and then once you know how to distinguish between lenses and non-lenses, you apply that to the rest of the data set and see if you can find more lenses. And yeah, they actually, even in this paper, which was now, it's kind of old from 2018, they found like 100 new lenses that were not discovered in this data set at all, just by using AI. I mean, you can do more complicated things, of course. I'm not going to go into detail, but there are more complicated algorithms that, for example, you give AI a pair of lensed image and a non-lensed version of it, so that it learns the mapping, how, like, kind of figures out how lensing works, how gravity works in some way, and then it can de-lens a galaxy for you. So you give it an image like this, and it gives you what the galaxy, the background, actually looks like. So these are some like preliminary first results of these sort of applications that I think are very promising, because they can actually help us see the galaxies that are very distant and very old. Okay, and an example for, I'm going to skip this because this is just a fancy version of detection. So let me show you an example for segmentation tasks. So now we don't want to classify the whole image. We want to classify every pixel in the image. So this is actually done by all of the self-driving cars and things like that, because the car needs to know very precisely where other cars are exactly, as well as all the lanes and all the pedestrians and all the street signs. So these algorithms need to do this in real time. They need to recognize every single pixel in the camera of what they see and be able to react right away. But we could use a similar type of thing in science when we also need to detect things exactly. So an example of that is to reduce some very annoying thing, which are called artifacts in observation. So again, dark energy survey telescope. This is how the field from this full image from the full telescope looks like. And you can see weird things in this image. You can see this circle, you can see this faint big circle, and these weird things here. Those things are unfortunate reflections that happen when there is a bright object at an unlucky location and create some extra reflections in the mirror. So you basically see kind of a reflection of the secondary mirror of the telescope. This is not really part of space. And so all of the pixels that you measure here are contaminated with this extra light. And you can't really use it to calculate anything about these astrophysical objects because they're contaminated with light that does not belong there. So we want to find all of these in an automated way. And we also want to precisely find them because we don't want to discard everything here, right? Maybe we have to discard parts here, but these here are clear. Like, why throw away this if we don't have to? So, of course, manually, what people did so far is just try to find these and just discard everything if there is any kind of weird small thing contaminating it. We don't want to do that. So we can train an algorithm like this one here to basically do that. And this is the actual result from our first try to do that, where we had classes like large faint blobs and small bright blobs and these things that are like spiky on the side and just had weird names we had to invent. But you can see, like in this example, it was managing to find all of these. So if we refine this more, we can do this very precisely in the future and do this really quickly. Of course, you can do a similar thing with astrophysical objects, which if they might be more fun for you than cleaning the data set. So you could give an example image with galaxy or star label, meaning each pixel in this image that belongs to galaxy has a value galaxy in it. So like that's why it's brighter in this. This is basically a label file. And for stars, all of the stars are also labeled and their positions are labeled in this label file. So this is a group that belongs to this one data point. And because here, instead of giving it a class galaxy, you're actually giving it a class, this is not working anymore. So you're giving it a class for each pixel. And it's the same type of training as when you're classifying the entire galaxy, but now you're trying to classify each pixel. So this group of researchers did a similar thing. So, and you can see that once the model is trained, it actually circles every object in this image, galaxy and star, and gives you a tiny number on top saying, this is the probability that I think this object is a star or a galaxy. So it's an automated object finder that is pretty good. And this is more than needed since we are going to have, in each image you have like millions and billions of objects. And the new telescopes are so good that actually, even though the space is pretty empty, the majority of objects in our new observations are going to be blended with one another. So you'll have stars and galaxies overlapping with one another, which is a huge problem because you want to find exact pixels that belong to one galaxy and exact pixels that belong to the other galaxy. So what do you do when they're overlapping? How do you actually extract physical information? So this is a very big field of research that we're trying to figure out. But as you can see here, if you zoom in, these type of objects can figure out that even though these things are overlapping, there are two objects there. So, hopefully we'll be able to refine them further to help us with this problem too. So to conclude, I wanted to say that for AI in astrophysics, cosmology, or any kind of science, there are definitely pros and cons. As you can see, they're like pretty powerful, but and they can allow us to work with huge data sets. But I want to point out the pros and I want to point out the cons, because for you, it's likely that you're going to be either building AI or using AI for work, whatever kind of profession you choose in the end. So I think all of us should be aware of all of these things. So as I said, AI is enabling us to work with huge data sets. It's much faster than any other type of algorithm or doing things manually. It learns from the data directly, so it avoids compound biases and your own opinions. So if you're labeling galaxies manually, if you label them correctly, incorrectly depends on how good of a day you have. If you're tired or you're sleepy, is this 1 millionth galaxy that you're looking at or just starting? With AI, you don't have this problem. You can also work with a lot more complicated data sets that maybe you yourself couldn't figure out on your own. And you can build models based on all of the data and all of the details of the data. But there are, of course, many cons that you can probably kind of expect when you hear I'm building models based on data. So that means that if I have a problematic data set biased in some way, the model is going to learn that bias, and it's going to be reproducing the things that are present in the training data that might be wrong. So you have to carefully think about the data and what you're giving as examples, because if there is a problem, any kind of problem there, the problem will be kind of embedded in your model. And if you're not aware of the problem, you're not aware that your results are skewed in some way. So that is the biggest, I guess, challenge, I would say, especially in science. I'm going to show you a non-science example of how important this is, so that you, from now to forever, remember this fact. So this is a data set called Labeled Faces in the Wild. It is made just scraping the internet for all of the news articles that contain some kind of face as a photo in the article. And it was made to test facial recognition algorithms. So algorithms that, again, now you have in your phones, so that you can it can know exactly where you are and put a filter on top of you, for example. And so you train a model to recognize faces, but the problem with this data set that nobody checked because it was big is that it wasn't very balanced. So what ended up happening is that 77% of all of the images were male faces, because that's just the frequency of how often they appear in news articles. And then out of that, 83% were white male faces. And fun fact is that President Bush had 530 images in this data set, which was twice as many as all the Black women faces in the whole data set. So that's ridiculous. So obviously this data set does not represent the human population. It represents the population of white males and President Bush. So you try to train a model to recognize all faces. It's going to be good in those where it's seen a lot of examples, but very bad at those where there were no examples. So this is what ended up happening. So the biggest companies that were training the most sophisticated algorithms tried to do this. And they thought that they were doing great because overall accuracy was great, because the majority of images were white male. But they ended up having 0.03% error rate on white male faces, but almost 35% error rate for darker skinned female faces. So if you had a facial recognition algorithm and you would train it like this, and you were a dark-skinned female, it would just not see you as a face. It would never put a filter on top because it just doesn't recognize you as a face, so this was really like a big deal at that time. And then they figured out what actually was going on, and they fixed the data set and fixed everything. But in science, it's not going to always be as obvious as this. So this is the tricky part. You have to figure out if you have a problem without knowing what the problem might be. So that's the problem. Yes, and so just to sum everything up, because this was a long talk of 2 hours, this is kind of what we were talking about. So the cosmology studies the whole universe. Astrophysics studies individual objects. That's the most important part from like the first part. The universe is around 14 billion years old, so pretty old. But everything else important, where things formed, happened kind of in the first 2 seconds and minutes. Today, universe is flat and expanding. The expansion is accelerating. This is the things that we see from observation. Everything that we see, like the observable regular matter, is just 5% of the things that exist in the universe. The rest is dark matter and dark energy. And today, as I said, we're figuring all of these things out using big telescopes and big simulations and AI today to kind of connect all of these puzzle pieces. So, of course, big data sets, as I've shown you in the previous slide, come with very big challenges. And in science, it's a lot more complicated than in industry. So machine learning can help with many things, but we have to be really, really careful in how we're building our models, how we're applying it, and planning in advance if we're going to use it on a similar type of data set as we're training or something else. So if it's something else, then warn that user that the model might not work as they think they will. Okay, thank you so much. Let's do questions.
All right, let's thank the speaker. All right, so we have time for a couple questions. I know we started late. You want in the front?
Could you elaborate on the universe being flat, possibly?
This is, again, a combination of theorists doing their theory of how things move around, so algebra, and observations. So the way the distances would work, depending on how distant things are, would be different depending on if the universe was flat or curved in any way. So again, it's not a fun answer, but it's a combination of theorists and observational work, and especially observational work that includes very distant objects like those exploding stars that I was saying, so that things are still, even very distantly, where we like kind of think there should be, basically.
So when I look at some of the images that were on the slides, all that I see is very low resolution, a couple of pixels. What can you get when all the data you have may be like a couple of pixels in a very small blob of galaxy?
I mean, yeah, the blobbier and worse the image is, it's the harder to work with it. There is, of course, some level at which things are too faint to be able to resolve. But for the majority of examples where we can figure out that there is an object there, it's good enough for an AI algorithm to figure it out. Even when things are fainter than what we would, see as an object, sometimes it works. So in astronomy and observations, there is usually something called signal to noise ratio. So like how many pixels of the object you have compared to the level of the background noise. And astronomers, when they were doing things with like their own eyes, they would have a cutoff value below which they don't want to deal with things. But with AI algorithms, we saw that in many cases, this bottom signal to noise can be actually lowered even further. Of course, at some point, it's just noise. So even if you try to find something, you should not necessarily trust it, but it's a good thing to maybe examine further or things like that. So you can do really noisy, bad things. You can find them, but it's of course much easier to work with nice images, which we have more and more of. But still, even in those images, you have many distant objects. So like the new telescopes, yes, they give you very clear, nice looking objects, but you have then a bunch more galaxies that are much further away, and they're still going to be just a 2-pixel thing. So, and yeah, we can still work with those.
One last question, anyone? Not. And thank the speaker one more time. So we're going to set up for our panel discussion. So we have two panelists here today. Signed in on my phone, so I hear myself, which I don't like. But yeah, so we have two scientists here today. I'll let them introduce themselves. So previously we had a panel that was about the everyday life, previously the panel was about the path to becoming a scientist. And the nominal topic of this panel is everyday life as a scientist. So as far as guiding your questions, I mean, you can ask whatever you want. But that's, I guess the topic that we had in mind. But yeah, I'll hand the mic over. So we have Adam and Josh that can tell you a little bit about themselves, and we can just get into the questions. But I'll hand it off to you two.
Good. I guess maybe we should start by just saying a little bit about what we work on here at the lab, by way of getting the discussion started. So my name is Adam Anderson, and I work primarily on cosmic microwave background experiments. These are measurements of what you can think of as the oldest observable light in the universe, the patterns of which we measure and can be used to infer really basic parameters about the universe, how much matter there is, how much normal matter and dark matter, the expansion history of the universe, and so on. And so what I work primarily on is actually the experimental design of those projects, deploying them to faraway places like South Pole, for example, and then the statistical analysis of the data that we take. So we sort of do, because the experiments are not, in some cases, not so big, we sort of do all aspects of designing, building here at the lab and deploying those instruments. And I'm also working on some other kind of detector R&D for different projects, not CMB projects, but using related technology.
And I'm Josh Barrow. I'm a postdoc here at the lab, working via University of Minnesota. And here working on primarily the NOVA and DUNE neutrino experiments. Currently the NOVA run coordinator, so I'm in charge of that experiment and everything on this month. And then I work in DUNE on what's called atmospheric neutrinos, baryon number violation, which is a cool beyond standard model that you can ask about later. And I work on other neutrino and electron scattering experiments previously and relations thereof. And I guess I've my second postdoc, and I've been at the lab here since January 2019, so I haven't left since then.
All right, so I'll ask the first question, and then hoping to see a lot of hands. Yeah, so I guess talking about everyday life as a scientist, what would you say that you do on a day-to-day? There's a lot of different physicists. There are a lot of different types of physics that you can do. Some people do theory, some people do experiment. Within experiment, there's, in theory, there's like a branch out. I work on experiments, so, mostly I work with hardware and detectors and analyzing data from detectors. Sometimes I do simulations. There's a lot of different, flavors of work you can do within, physics. But I'm curious about, how you spend your day-to-day life. You wake up, have some breakfast, head to the lab. What are you usually working on these days, at least? Because I know it changes week to week, month.
Yeah, so I can give two answers to that. Well, maybe I'll just give one answer, which is, I think that I work in a lot of different ways, depending on what particular project I'm working on. So I spend a ton of time in meetings talking to people, which sounds really boring. I also spend a lot of time actually doing stuff with my hands in the lab. I spend a lot of time writing code on my computer, writing emails, and sometimes I find myself, in Antarctica, deploying experiments. So the things that I do in a given day very much depend on what stage the project is in. If we're building something, that means it's very much more hands-on. Or if it's not my hands on it, it's postdocs who are working with me, for example, or graduate students. On smaller projects, you tend to work on more things that are in the lab, but on bigger projects or projects that are already taking data, you just tend to spend more time in meetings or analyzing data. So I would say I work in many, many different modes, but it very much depends on the details of the particular project. And I think that's one thing that makes our type of scientific work interesting is the day-to-day activities are really varied, and you do whatever it takes to, answer the questions you're interested in.
I completely agree. I work in a bunch of different modes depending on time of the particular day and the particular day of the particular week, and it changes week to week and month to month. There's a lot of variety, I would say, and that can be simultaneously stressful and meaningful and interesting. And back in November, we decided to replace a gigantic set of components on our near detector here at the lab, 100 meters underground, and organize like 15 people working and getting travel organized for people to come here and do work. There's project management that goes into that, and then also getting to go down there and get your hands dirty and work on a detector is kind of fun. Or like right now, the project I'm kind of leading is a brand new machine learning project that none of us know anything about, and we're kind of moving through the dark together and trying to figure out what we should be doing and how we should be learning and thinking about these problems. And otherwise, I run meetings and advise students and do a little bit of coding still and things like that. But a lot of it is just sitting down and talking to people and trying to understand what their problems are and what you want to contribute to their solutions for those problems, and trying to understand what other people are interested in so that you can bring them into whatever scientific group you're working with. And that's a weird thing to say, but it's not always just coding and solving problems on your own. A lot of group interaction in that case.
Can people hear us on the Zoom okay? Okay. Oh,
I was trying, because I logged in on my phone and then. All right. Questions in the room. All right, we got one right here.
So I know that you mentioned finally with going to Antarctica, but I was curious, how often do you actually leave Fermilab?
Well, I mean, pretty often. I think depends what you mean by leave. So I think most of us travel quite a bit to go to conferences or collaboration meetings, meetings related to projects. How often? I don't know. Once, in my case, probably once every couple of months, I go somewhere. Sometimes more often, sometimes less often. With the specific case of Antarctica, which is a little bit unique, you can only go to work there during the austral summer season. So that happens once per year. And we would typically go for anywhere from 1 to a maximum of 3 months, because the austral summer was only 3 months. So yeah, so that's, for me, roughly how often I travel is once every couple of months.
Yeah, I similarly travel relatively often. I just learned like 2 days ago that I went from having 0 conferences or workshops that I'm attending to 4 in the next 5 months. So those kinds of things can change really quickly. And sometimes there's collaborators that you're working with around the world, and they're kind of like, hey, we need to get together to work in person. Let's find someplace either here or elsewhere that can easily accommodate a lot of people and get ideas kind of springing to life together. Really important. Yeah, I mean, we travel a lot, depending on what the experiments are. So, like, I'm going to be going to the Dune Far site and going a mile underground and looking at the caverns that we're going to build gigantic detectors in. So maybe not as nice as Antarctica, but still kind of cool and novel. Get to do a lot of those kinds of things when you have a large collaboration kind of spread around the world and experiments are everywhere.
What are some of the cons or disadvantages of working in physics?
Well, that's a good question. I think probably the one that most people would say, which I think is true, is sort of career stability. So, you know, for whatever reason, the supply of people who want to become academic scientists exceeds the number of available positions. And so what it sets up is this situation where you have, at every stage, a lot of people competing for a small number of jobs. And I think for many people, that's very stressful and can be disappointing at times. And so that's probably what I think most people would say is the biggest con. There are two flip sides to that, which is, for whatever reason, we've set up this system that sort of do make it through all these hoops. At some point, you actually do have quite a bit of job security, you know, because you're a tenured professor somewhere, or you have a permanent position in the lab, whatever. So that's kind of the flip side. And then the other flip side to that is that, you know, when you are trained as a scientist, whether it's physics or really any other field, you acquire a lot of really useful skills, right? That are not just useful for solving research problems, but they're useful for solving problems in any field. I kind of like to think of being trained as a scientist as being trained as a professional problem solver, where those problems can be totally generic, right? You're not trained to specifically solve a certain type. And so that makes you very valuable to companies and in industry. And so it's correspondingly, you know, not so hard to get a good job in industry if you decide you don't want to go into research at any point in your career. So yeah, so I think that's the biggest con, but it's sort of, the caveat is, I think basically everyone who gets a PhD in the sciences does pretty well and has an interesting, more or less interesting job at the rest of it.
The other way I'd say that kind of is if you have a PhD, and particularly in something like the physical sciences or mathematics or computer science, what you tend to be is some kind of a systems theorist. And basically that means that you're thinking about how to think about problems, how to model things, and try to put them out and test them in the real world. And that's a very good set of skills that's very marketable. As far as cons, we PhDs takes a long time to go through that. It's comparable in training with postdoctoral experiences to becoming a medical doctor. In medicine, or in school, and then you're in medical school, and then you're in fellowship and residency, other things. 10+ years sometimes. And nowadays, similar physics or other similar sciences, it's a similar period of time. So there's obviously a bunch of capital that in principle you're missing out on if you, for instance, have an idea to start a company, or you have a certain marketable set of skills already that you can move into the private sector or convince somebody to fund your ideas. So there's some things that you miss out on in some respect there. But I would say that for those of us who are kind of interested in these kinds of endeavors for just the sake of the questions themselves and trying to learn more about the world, it's pro. And if we don't get compensated similar to our perceived skill sets in the private sector, of course, you can make a lot more money, but still very meaningful for a lot of us here when we choose to do science over that.
You're good. There's one on Zoom, and then I'll get to you. I was going to tack on. I don't know if you've heard of the term opportunity cost.
Yeah.
It's a good term. I mean, it's an economic term, but it's like that's the big thing with the PhD. Like I remember being in grad school and like, I studied astrophysics undergrad, and then one of my like closest friends from undergrad, he went to work for a hedge fund, and I'm eking by in New York, paying rent. I'm 3 or 4 years into grad school, and he like gets some big bonus and he buys a condo, and I'm like, when am I gonna be able to make those like big life moves? I mean, but it is basically like getting a PhD or getting an MD or any of those things is like basically investing in yourself and investing in your own education, and then hope the ideas down the line you'll get some payout for it, which so it's basically a lot of time and opportunity costs. But yeah, I like working in physics, like working in science, like working in if you work for a company, you have to make money. That's the bottom line. Where I like being in a space where we're trying to produce knowledge and tinkering with things, trying to figure things out.
Not to belittle the cons, but more pros. One thing that is really nice about graduate school particularly, and if you do this in physical sciences and you have the opportunity to be really a supported young researcher pursuing a higher degree, you're getting a stipend, things like this. There's a real incredible amount of freedom intellectually that you're given the opportunity to pursue. I never believed them when I was talking with people in undergrad. It's like, oh yeah, no, you're gonna have more time than you've ever thought you'd have to learn more things than you ever thought you would know, and that is a really enriching thing. And sometimes squeaking by just above the poverty line, but given that freedom as a society, that we're basically saying, take our tax dollars and let these young people pursue these things, is sometimes arguably enriching, not for just the individual, but for the country as a whole.
We'll do this one from the Zoom, which I think is a good question. So what is the biggest advice you would give to your past self, / what is something you wish you realized earlier?
Well, I think I did okay in this respect, but one advice I like to give to people who are very interested in sciences or math is that there's a tendency to, when you're taking your classes, and particularly in college when you sort of get to choose what you take, there's a tendency to just like be very single-minded and only focus on taking like math and physics classes and training your mind to think in that way. And I think that as really as anyone, but in particular, in industry or in research, but in particular in industry, in research, as a sort of someone who's a scientist, having the ability to communicate clearly, both speaking and writing, is very, very important. It's as important, actually, as your ability to solve technical problems. And so, doing things that improve your communication skills, learning how to write clearly, how to make a reasoned argument clearly, convince people who are skeptical of you, all of those things are not really actually things you learn in physics or math classes. They're things you actually learn more in humanities classes, but they're actually equally important to being successful as a scientist, because your ability to do work is contingent on your ability to get funding to do that work, your ability to motivate and inspire people to work for you. And you can do those things by being technically compelling, but you can do them like 10 times better if you're persuasive and can communicate well. So I think those skills you should always try to cultivate, and they will serve you well even if you go into industry, right? If you start a business, you know, being able to persuade people to give you money is also important. So that's my advice.
Biggest advice you would give to your past self is something you wish you realized earlier.
I agree with everything there. I did a lot of writing in high school and loved it, and really went into a writing course. And then I physics, ironically. But point being that I would say my biggest regret, at least from undergraduate, was I did not do enough computer. Definitely, compared to my colleagues, I would say behind curve in many ways. I'm doing my first machine learning project I've ever done myself, as in like I'm actually responsible for certain elements of the coding and not just like the data set production, things like this. So the more that I think you can do that kind of work early on, the coding skills you have, the more abstract languages you can understand better, I would say. As far as other kind of regrets, I would say, I don't know. I did not make enough time in graduate, especially definitely in high school for friends, and I did make time for family, but I didn't make enough time for friends. And so I would say making sure that you can have that kind of balance is wonderful if you can. That being said, again, there's 10,000-hour rule, which you probably have heard about before. The faster you can get that kind of into your brain, the better. But if you can do it while also maintaining a well-rounded sense of humanity in and of yourself, as talked about by better. So it's a balancing act.
I'll tack on to that. Well, just being organized was never my specialty. I'm realizing how important it is. I mean, I was always able to get by, you know, I don't know, not harm, just like, you know.
You're so charming.
I was able to get away, or like, oh, I'm so sorry I missed this. Like, could you just give me like an extension or blah blah blah. Like I feel like, I mean, obviously it helps if you go to find a university or college or high school, you know, school that has good support systems that, you know, can fall back on. But I just feel like I only like really started this year keeping a calendar, and it's just like made such a difference as far as like, I mean, I was somehow able to keep track of most things in my brain, but then things slip, like just like little things like keeping a calendar, taking notes, just make a huge difference as far as like getting stuff done on time and with low stress, and being able to like have a social life as well as like a work life. You know, just staying organized helps, you know, make your life that much easier and happier, better. All right, question.
So I guess kind of related to that, how often do you find yourself doing physics or doing your work outside of work hours? Or like when you go home, are you still working on physics? Or are you just like, okay, work's over?
Ask me when I said you should ask me when I'm not run coordinator right now. So I'm on call right now 24/7 this month. Doing that 1 month on, 1 month off for a year. I'm 6 months where I can be contacted at any time if something is wrong with the experiment principle. Now, luckily, I work for an experiment that is about 10, 11 years old at this point. It kind of runs pretty well. We figured it out. But there are other experiments right now that are in commissioning phases that it is hell on earth for a lot of people. There's something called the Icarus experiment. Best friends flies in from Italy, has 3 months as Runco. I swear to God, he does not for those 3 months. But that's because it's an kind of newer detector. It's still in this commissioning phase, but he also loves it. So that's one of the things that he's crazy enough to want to do that. And he's Italian, so he's definitely crazier than some of us. But point being that he's willing to do it, and he loves being here and solving those problems day in and day out, trying to get the thing to work the way that the collaboration wants. So the answer is we do think about things outside of work hours.
Yeah. But the other thing I'll say, so definitely agree with all that, and I agree also that the extent to which your schedule is inflexible depends on what happens to be going on. And yeah, if you're commissioning a new experiment, it's crazy. Definitely have had that experience before. Where was I going with this? Oh, right. But I think that to some extent, you have some control over this based on what types of things you work on. So for example, I think that it's probably true that every professional scientist spends a lot of time outside of working hours thinking about problems. Partly that's because they really care about getting them solved. It's not because there's some outside force telling them you must work between, the hours of 9 p.m. and midnight. And so you have some degree of flexibility based on other commitments and the type of project you're working on. And, to some extent, I would say people who work in theory, for example, probably have a little more flexibility because they're not on the hook for delivering things for a project, big hardware project on given timelines. But I think if you were to ask them, how much time do you spend thinking about physics outside of work, they would say they're always thinking about physics, whether they're going for a walk or whatever. So yeah, maybe that's not a very clear answer, but I think that, you get people who are intense in a room and they start, they have a hard time letting go of problems, maybe.
So I don't think any of you are old enough to go there, but one of the great things about Fermilab is that Fermilab has a user center with a pub inside of it. And so one of the things that have sort of spurred on the creation of this thing back when the lab started in the late 60s, early 70s, was that if you work hard and play hard and you do it together, better. So sometimes when you have your 8 a.m. or 9 a.m. to 5 p.m. period, a little bit of a structure there, but you go and you're around your friends and your colleagues and you loosen up a little bit, then you can solve even more problems sometimes. A number of times I've had that happen where you are outside of working hours, you're having fun, it's a very relaxed environment that you self and exchange ideas. Like that can be incredibly enriching still. So that being said, it's usually slack at 9 p.m. or 10 p.m. right before I go to bed, and it's sad. But
I would say it depends on the person. I would say most people, it's not a 9 to 5, and work kind of bleeds into the. I knew someone in grad school that was able to do a 9 to 5, but they were ate lunch at their desk and it didn't stop during the day. I like to, I don't know, go for a walk and I don't like waking up early, so it ends up going into the evening for me for sure. But it's stuff that I'm interested in, stuff that I like to think about. What else there?
Yeah, there are people that do actually pull that off. We're pretty regimented, and yeah, and I think make it. If people are very disciplined, they can be quite a bit more structured about their time than, for example, I did in being. But no.
So I don't know if it's dark energy or your pure love of physics, but what prevents burnout for you guys? Have you had any burnout?
That's a good question. I don't know if I mean, yeah, at various times, probably I have been a little burned out. Yeah, I mean, I think that the key is there are definitely people that do burn out, but I think the key is making sure and maybe this is just a totally generic answer, and so it's not very helpful. You tell me. But like with anything, if you can like realize when you're just like not having fun, the work you're doing is not enjoyable, and try to have some kind of break from that, I think that helps. I think the one thing that maybe makes that doable in our field is the fact that there are a lot of different things to work on. And, if you're getting really burned out commissioning an experiment, well, at some point, the experiment will be commissioned and you'll be taking data, and then you can switch to doing analysis, which is a very different form of working. And having that variety, being able to change what you're working on, can help kind of re-energize you. And the fact that most of us work on multiple projects, right? So if one project is really a drag, there's a good chance that soon you'll be able to switch to working on something else, or maybe you're also working. But it is a struggle in any activity, not just work, right? In any activity in life where really consuming a lot of your time, sometimes that can make it not fun anymore. I don't know.
Yeah, so I think there's definitely people who burn out, and I would say that it's predominantly people who don't have enough variety or novelty in many cases. There's graduate students that I've known before where their professors are a little bit too hard and going too quickly and not allowing them to kind of expand their own kind of visions and explorations of physics. That can be really, I think, detrimental just for like, for lack of a better term, like the soul. And that can lead to some burnout. I think that whenever I feel that kind of burnout coming on, where I've been hammering myself on a project or a problem or something like that, one thing that I always love to do is go and have coffee with someone who I respect and love how they think, and that just kind of reminds me and kind of recenters me about why I'm interested in what I'm doing. Because sometimes you can lose the forest for the trees when you're down in the depths of one of those problems, and doesn't feel as enriching as it once did. But that can be really helpful. I think that being able to have that variety of problems, though, go and work on hardware and work on some analysis and advise people and mentor people can be great, just because it keeps you on your toes. The other thing I would say is, I know you guys are young and you've probably heard this a million times, but wake up at the same time every morning unless it's weekend. Set a schedule. It just helps, at least me personally, for sure. Whenever I'm kind of in a weird mood or down in the dumps, I force myself to do those things. It usually just helps me, not just with my work, but with my overall kind of feeling about life in general. So.
I'll also say like having some like hobbies or like exercise is also good. And a lot of time running, biking, that's a great way to like refocus your mind. Everyone does different activities. Finding an activity that has nothing to do with physics that you can do for an hour anytime is
Really something where you don't have to think. Or I like playing soccer because it's like I just have to react.
yeah. Thinking in a different way.
I think we had one there. What was I gonna say? Well, I think it's all. I like to travel. Like going on trips, I feel like, or taking a couple of days off, I feel like revitalizes me. It's good to like make sure you take time for yourself. In general, like once a quarter at least, I try and go somewhere. If it's for a conference, great, because the company pays for it. Otherwise, I can visit a friend or go camping or something. But it's good to try and make sure you take time for yourself. You have a question?
Despite the amount of work it takes to be in the field, what would you say is the best part of working in physics?
So I originally was going to do biochemistry. I wanted to do HIV research. I wanted to do PhD, MD. And then the research bug caught me because I gave a weird talk at a gala for basically trying to fund the university I was going to. A scientist who was in the audience there, one of the physics professors, came up to me and said, "I want you to work for me." No idea who this guy was. And then I worked with him for 2.5 years. Toward me, and worked side by side together on a quantum chemistry project, several papers, 8 hours a week, where we were completing each other's sentences by the end of it. That was my first experience with true mentorship. And I would say, me, the two things that are best about it are collaboration and mentorship, because those can be, they're just incredibly meaningful when you're able to solve a problem together or influence really the trajectory of someone's life in kind of an interesting and fruitful direction. I think that's really helpful. So in some respects, you can do that in any field. I, of course, like the field that we're in, where we're doing that with kind of fundamental problems sometimes. That's, to me, the most enriching, but there can be others as well, of course.
Yeah, I totally agree with that. And I'll say two more things, one of which is kind of related, which is I think one of the great things about scientific research is with people. So like all the people we interact with, work with, are incredibly talented and interesting, and oftentimes quite difficult to deal with. But just like the sort of caliber of people that you get to work with and learn from and interact with in scientific research, even if they are difficult sometimes, is really great, and it's just really fun to be around and learn from your colleagues. And then the other thing I'll say, which is maybe, which I really like, is this idea of like building something or designing something, building something, and then making some measurement that it seems like it just like shouldn't work, and then somehow the data pops out and you see this thing that it's like very abstract, but you just see it so clearly in the data. So like the example of this is, we built this camera for very, state-of-the-art camera for observing the CMB. And we spent all this time, literally, I was spending hours just like turning screws to put stuff together, like incredibly mundane work in many respects as a postdoc. And then we deployed it, we put it on the telescope, and we're sitting there, and trying to make it work, and it's just dealing with all this mundane crap, like noise and the amplifiers, electronics not working. And finally, we sort of got it working, and we, run our quick analysis, and boom, there is a map of the CMB, right? This light from 13 billion years ago, and you see it so clearly. And what's amazing is like all this, you do all this work, all this, complicated stuff that seems totally divorced from this very abstract thing you're trying to measure, which is very hard to measure. And then at some point, it just all kind of works and agrees with the theory. And that's like a really, really, for me at least, an incredibly satisfying feeling of the idea of building something and then being able to do like a state-of-the-art measurement of something that is very difficult to measure, from which you can learn something new about the universe. Maybe that's an experimentalist answer.
So we're almost at time. There's one question on the Zoom. I forgot to mention the eclipse. I feel like I would be remiss to end the session without mentioning. There's a full total solar eclipse happening on Monday. You can get to Indianapolis is probably the closest place. It's a spectacle. I've never experienced this. It's a bucket list thing. Might be cloudy, so who knows? But I'm planning to drive to Southern Illinois tomorrow to try and catch it. The next time, I guess, a full solar eclipse will pass over, the United States mainland will be 20 years from now. So it's kind of, if you can, see it or get your parents to to drive you down, take the day off school, I would say it's worth it. But that's just me.
Forecast is good.
Forecast is
70
good.
degrees and sunny on Monday.
All right. And you can see partial, like if you get like eclipse viewers, you can see, even from here, you can see like little kind of like a crescent moon on top of the sun. But you need to get like stuff, I forget what they call them, eclipse glasses, because if you stare, it'll hurt your eyes if you look at it. The shadows look cool for the partial eclipse.
I was going to say, just like get a piece of aluminum foil, poke a hole in it, and have a pinhole camera.
Yeah. I guess we can maybe address this really quickly and then adjourn, but does having a double major benefit you in your work? I don't know if either of you were double majors or.
So I did a BS in physics, a BS in math, a minor in chemistry, and a minor in biology, just to keep my options open. I actually initially wanted to, when I started doing physics and I switched from biochem that I had mentioned previously, I was bored with biology, particularly because I hadn't covered genetics yet, or epigenetics. When I initially did physics, I wanted to be a teacher, and at least where I'm from Tennessee. And in Tennessee, if you want to be able to teach any high school math or science, all you are required to have is a minor in an undergraduate degree to do any kind of teaching there. So basically, I had a insurance policy before I went into research. So short answer is that I think that kind of broad exposure to science as a discipline was really helpful. It's also just great as a party trick to start pulling out stuff about genetics or other things that people don't think that you should know about, and being able to actually have a conversation. But also, especially with the math, I would say it only encourages you to go deeper into kind of the understanding that you would want to have for how basic physics really happens, fundamental physics really happens. If you ever want to look up something that's crazy, look up something called Sturm-Liouville theory. It's probably the deepest set of math that I know. Sturm, S-T-U-R-M, Louisville, L-I-O-U-S-V-I-L-L-E. Basically, it's the connection between partial differential equations and quantum mechanics, or operator theory in general. That kind of ability to understand things from being given a broader set of skills is always helpful.
Yeah, so I also majored in physics and math, and I think that the act of having a major versus just taking a lot of classes in a particular area is maybe there's not such a big reason to necessarily major, but obviously a lot of people do both math and physics. For me, the thing that was most useful about that is that when you major in math, of course, most of the classes you take are writing proofs. And the thing that is valuable about learning how to rigorously prove things, write proofs, is that it teaches you extremely careful reasoning. In other words, how do you go from a set of basic assumptions to a conclusion that is absolutely true, which you have demonstrated? When you take physics classes, when you take science classes, oftentimes, mathematicians, they hate physicists because they think they're not rigorous. And it's true. And the reason it's true is because physicists don't need to be as rigorous. But having training in how to train your brain to be just extremely, extremely careful and understand all of your assumptions and how they lead to a set of conclusions, that is super useful. And I think that's even useful outside of the sciences. Like people who go into law, for example, use this kind of reasoning, sort of deductive reasoning. So for me, that was what I took most from training in mathematics, even though, frankly, I don't do very much formal mathematics at all anymore.
Just remember that the converse is not the contrapositive.
Yeah, right.
And if is not if and only if.
Yeah.
They're actually incredibly important because there's few things that you will automatically start noticing once you take a real set theory and logic class. It's impressive how many different fallacious arguments you find in all kinds of politics and things like that. You want an interesting exposure to that kind of same logic, you should read Paradise Lost, which talk about humanities. Great education in both logic and also rhetoric. But anyway, I would also just add, I think the best thing about physics, right, which is the exact opposite of mathematics, is you learn to make approximations and how to defend your approximations with fallacious arguments.
Yeah.
So it's two sides of the same coin, but they're both incredibly useful.
All right, with that, a little bit over, sorry, but I hope it was good, enjoyable. Maybe you learned something. So next week is our last week. It's graduation. Your parents are welcome to come. I think we'll be in this room. We'll follow up with more details. Chance we're in Ramsey Auditorium, but I think we're scheduled to be in here. But yeah, looking forward to seeing you all, get certificates and stuff. So it should be a nice last session. We'll have a talk from the director of the lab, Leah Merminga, about physics and society. So it should be a nice talk. And yeah, although there will also be snacks and food, I'm pretty 95% sure. Spence, you know, I think Spence is gonna make it happen. I think you can hear me right now. Well, all right, we'll see you next week. Have a good one. Have a good week, and catch the eclipse if you can.
Thanks very much.